Okay, welcome to lecture. We're continuing on talking about complex ions, coordination compounds, transition metals, all that good stuff. We'll get started here in just a sec. Okay, so remember that we did a little switcheroo. So today, again, the exam is not today, it is tomorrow. And we're going to have a regular lecture today, and we are doing group 4, group 5. So I think this experiment 2021 for lab today. So again, we sort of swapped those two things. And so in lab later, that's what we'll be doing. The final sort of group there before our general unknown. Okay, so we started talking about, just to review, go back a little bit here. We started talking about complex ions really and coordination compounds. We talked about transition metals, obviously, before that, along with a little bit of, maybe some of it was review in terms of properties of transition metals and things like electron configuration, ionization energy, and those type of things. And really the purpose of that is just sort of review, but also because a lot of complex ions do involve transition metals that are involved. So we do see some of that properties that are important to remember. So when we talk about coordination compound, as we talked about, there really is two parts to a coordination compound. There is a counter ion, and there's also a complex ion part. The complex ion part is typically the part that does have that transition metal that has a number of ligands that are attached. And remember, ligands are Lewis bases, which means that they can donate a pair of electrons to the metal, which is sort of electron deficient, and they make these complex ions. Now, the complex ion can be a positive ion overall, and the complex ion can also be a negative ion overall. And that's really where the counter ion comes into play. The counter ion is essentially really there to balance out the charge. So if you have a negative complex ion, you will have a positive counter ion to balance it out. And vice versa, if you have a positive complex ion, your counter ion will be negative to balance it out. So really, coordination compounds could be thought of almost as just ionic compounds. Basically, the overall charge, when you sort of put that together, does need to equal 0. So everything should equal 0 in that sense when you take all the positives and all the negatives and put them together. We also talked about figuring out the oxidation number of our transition metal in the complex ion. So you sort of approach that the same way as we do other oxidation numbers and sort of figuring those things out. So the other important thing as well is within a complex ion, there is something known as the coordination number. And the coordination number is how many donor atoms are bound to the metal in the complex ions. So remember, though, that our ligands can be, in some cases, monodentate, which means for every one of those ligands, they attach with only one atom to the metal, like actually the example that we have here, hydroxide and ammonia. They're all monodentate, which means basically for each of those, you get basically one atom that binds in. And that's why when we look at our first one here on this slide, the coordination number is 4. And that's because the oxygen in each of those hydroxides each basically bind to the metal and giving a coordination number 4. While on the other side, we have ammonia, which each will bind in through the nitrogen in ammonia. And since there's 6 of them, gives us a coordination number 6. Remember that not all ligands are monodentate. Some can bind in more than one place per molecule. And we talked about a couple of those here on this list that we saw. Something like oxalate at both of the oxygens can bind to the metal. So for something like oxalate, it's almost like a 2-for-1 situation where for every molecule of oxalate, you get 2 atoms that bind in there. So you get basically a coordination number of kind of 2 for every one of those. Same thing with that ethylenedyldiamine or that EN. Also, again, the 2 nitrogens there can each bind to the metal, and again, giving you a coordination number, basically 2 per, if you will, for every one of those that you have. We also see some that are polydentate, which means they obviously combine more than 2. So there's diene there, which can bind in 3 places at each of those nitrogens. And then we talked about EDTA, which again has 6 different locations as to where it can bind, which means, you know, essentially the coordination number would be 6 there with our EDTA involved. We just had one of those molecules. So sometimes you do have to adjust. And as we talked about, really where that comes into play is very often people will sometimes just sort of look at, you know, sort of the subscript and go, all right, well, the subscript here is 4, so the coordination number is 4. Subscript here is 6, which means the coordination number is 6. And in some cases, that may be perfectly correct if it is monodentate. But again, if it's bidentate or something like that, it may not be correct. So you do have to adjust for that. So when we figure out these sort of things, remember when we're kind of doing the oxidation numbers here, we have something like hydroxide, which we know hydroxide OH overall is -1. And again, there's 4 of them, which gives you a -4. On the outside is potassium, which group number 1 has a +1 charge. And that gives you -4 and +1 gives you -3. And again, to balance it out, the gold in that case would be +3. So remember that when we go about sort of figuring out these oxidation numbers, we do need to make sure everything equals 0 when it's all said and done. Then at the end last time, we got into sort of the rules of naming some of these coordination compounds. And there's a lot of kind of interesting rules that we talked about in terms of naming. I'm just to kind of go over those one more time here at the beginning, since that's sort of where we left off. Again, like a normal ionic compound, we do our positive guide, then our negative guide. So our cation first, and then our anion. Again, that goes both in terms of formula and also the name as well. When you go to name the complex ion part of a coordination compound, we do put all the ligands in alphabetical order, regardless of the prefix, actually. And then we always end with the name of the metal at the end, along with a Roman numeral. So again, as I mentioned last time, it may be more clear as we start getting into naming some of these guys. But when we talk about finishing with the name of the metal, again, it's really just for the complex ion part of the name, which if the complex ion is positive, that will come before the end of the actual name. And if it's negative, it will come at the end of the overall name. So we'll kind of see that as we go along. So it's not just that you should put the metal at the very end of the overall name. It may go there, it may not go there. Some of our negative ligands have some names. So water, for example, aqua or aqua, amine for NH3. We also use prefixes if there's more than one ligand within a coordination compound or even a complex ion. We use di, tri, tetra, penta, hexa for 2, 3, 4, 5, and 6. And the weird thing is, again, if the actual ligand itself has that prefix in it or a prefix in it, a Greek prefix, actually in the name, we then kind of go and roll into different sort of prefixes like bis for 2, tris for 3, and tetrachus for 4. And again, the example of that we looked at last time was actually this guy right here. Again, when you look in the name, you can see it actually has, as I wrote over here, it has the di part of it in the actual name itself. And again, that means that when we have more than one of those guys, so for example, if we had 2 of the ENs, we would not use We would not use di, we would use bis to represent that because it actually has the name in it to begin with. We always, again, as I mentioned, end the complex ion part with the metal name. We also always include a Roman numeral for the charge on the metal. And again, some weird things that we kind of do here with coordination compounds that we don't typically do with others is things that have sort of fixed charges that are still transition metals, things like silver or zinc and stuff like that. When you're kind of doing coordination compounds, people do typically still put the Roman numeral, even though it's sort of fixed. And as odd as it may sound, I think in the lab that we'll do, I guess it will be Thursday, you'll come across some that will even have an oxidation state of 0. And you sometimes will put 0 there in the parentheses like you would for the Roman numeral. So there's a few kind of interesting things that are sometimes included in these sort of naming that we don't necessarily do in sort of typical nomenclature when we do that. And then the last sort of different thing is if that complex ion part of the compound, of the coordination compound, or just the ion itself is negative, then we kind of go with the older way of naming it, and those are like the cuprate, plumate, stannate, those guys that end in ate. If your complex ion is positive, you can just go with the regular old name, and you don't have to worry about it. You could just name it like normal. Any questions on any of that there? And these were some tables here of some of those things, again, are sort of older way of naming things as we see here. And some of those ions in their names as well. Again, you need to be familiar with these. So for example, let's take a look at this guy to kind of see what's going on here. We got a lot going on with this guy, and it is a hydrate, so that dot actually should be like right there. So if you're familiar with hydrates, right, there's usually a salt. It usually has that little dot and then some waters associated with it. So that's what we're looking at here. So that little guy on the bottom, you should get rid of it. Actually should be a dot like that in between. And what we want to do is sort of dissect what we got going on here. And we actually have a lot more going on here than you normally would probably see. So for the time being, we're just going to kind of ignore the hydrate part. We'll get to that at the end. So we're just going to kind of focus here on the front part of it. And we want to kind of sort of figure out certain things. First off, as we talked about last time, typically speaking, within your bracket there is your complex ion, which by default means that this guy here would be my counter ion. And now when we look at this, just sort of the arrangement of those two things, it should tell you a couple of things that's important. First off, it should tell you because the counter ion comes first, that's got to be the positive guy. And my complex ion comes second, which means the overall complex ion has to be negative in that particular case. So we want to sort of figure out some charges, perhaps some oxidation states. So this is oxalate, and oxalate is a -2 charge overall. There's 3 of them, which gives you a -6. On the outside, that's potassium, which is +1, and there's 3 of them, which gives you a +3 overall. Remember that these coordination compounds do equal 0 when it's all said and done. So I got -6 and +3, which means the chromium here should have an oxidation state of +3 as well. And that will give me +3 and +3 is +6. And when you add that to -6 gives you 0. So that's important. Our chromium has a +3 charge. Also important is how we go about sort of naming this part of it. Because our complex ion is negative, and just to illustrate that for you so you can see that, we just figured out that the chromium in this setup is +3. And the oxalate overall, -2, gives you -6. So the complex ion part itself has an overall charge of -3, which is why it is the negative part of it. That also explains over here why we have 3 of these potassiums, because to balance that out, we need 1, 2, and 3, +1, +2, +3, balances out the -3 overall of that complex ion. So these are sort of our components. Because our complex ion part is negative, that means when we use the name for this guy, we need to use sort of the old school name of it, the one that ends with 8. So we would not use chromium in this case. We would actually use chromate, because the complex ion part is negative. So we go from chromium to chromate, and we would definitely include the Roman numeral to indicate the charge on it, which is 3. Any questions on that so far? I found the oxidation state on chromium, if that's what you're asking, is the oxalate has a -2 charge overall, the C2O4, and there's 3 of them, which gives you a -6. Each of these potassiums, as I laid it out over here, is +3. So +3 and -6 is -3. So it has to be +3 to balance it out. It's a very good question. Let's talk about that. We'll get to that. But the coordination number here would be 6. You would be correct. The coordination number is 6 in this case. And that's because oxalate, as we talked about earlier, both of the oxygens could bind in. So that's basically a 2-for-1 type of deal. So every one of those molecules of oxalate will bind twice. And since there's 3 of them, the coordination number here would be 6 in this case. So this is also a very good example that it's not always, you know, the little subscript there for the coordination number. Okay, I think I got everybody's question there. Yep. Okay. So we do have 3 oxalates here. And remember that if we go back to the little table for oxalate, that is called oxalato as the name for oxalate. And I spelled that really bad. Let me try that again. I wrote T instead of L. There we go. Oxalato. Yes, there we go. So that is oxalato, which is basically oxalate's name. Now, there are 3 of them. If you remember the other day as well, yesterday, I did mention that although oxalate doesn't appear to have sort of a prefix in it, it is one of those that people will sometimes consider having a prefix. So people will use tris for this guy sometimes because it's oxalate, or you could use tri in this case. Either one would technically be okay. And the tris or the tri, and again, the tris here is kind of weird for oxalate. People tend to use it with it, but you could use tri in this case. It would be okay. The tri is because there are 3 of them. Okay. So now we need to think about the first part of the name, and the first part of the name may also be kind of confusing as to maybe what we end up with. But what we end up with for our counter ion is really just the name of the counter ion, which is potassium. So we will start with potassium, which is our counter ion. Now you may say there's 3 of them. Do we need to put anything in there for the 3 of those? You do not for your counter ion. So it's kind of similar to if you had, let's say, K2O. You would call that potassium oxide, even though there's 2 of them there. You don't put like dipotassium or anything weird like that. So it's kind of similar to that. If you have that guy K2O, you would call it potassium oxide. So here we would just use potassium, even though there are 3. And that typically is the case with your counter ion. Even though if you may have more than one of your counter ion, you typically will only just kind of use the name of the ion, be it a positive or negative counter ion, typically just the name of it. Now we want to start with our ligands, which are these guys. So you could end up with putting all this together: potassium, tris, oxalato chromate, Roman numeral 3. And this is what we're talking about in terms of the metal coming at the end of the name here. This is the end of the complex ion. I'll just underline it. This is the complex ion part of the name. At the very end of the complex ion part of the name, we have the metal and the Roman numeral. And we kind of ignored the hydrate part at this point, but as you might remember, to name hydrates, you used prefixes as well, and hydrate for water. So there's 3 of them. This would be trihydrate. And this part of the name is a little unusual. You probably won't come across too many hydrates, but happens to be in this case. Again, the trihydrate here is for the 3 waters part of the hydrate. Also acceptable in this particular case, because it is oxalato, you could do potassium trioxalato chromate 3 trihydrate. With a little flare there on the hydrate part. There you go. Question on those names there. All right. In this particular case, it will be the last part of the name because it's a hydrate. I'll be honest with you, probably 99 times out of 100, you probably won't come across a hydrate in this coordination complex or compound. But because it is, in that case, the hydrate would typically always come at the end because of that. And again, the tri is just for the 3 waters that are there, and instead of water, we use hydrate when we name it. But probably very rare in most cases in terms of hydrates coming across here in these coordination compounds. So kind of a rare one, I think. Other questions on that? Okay, so a lot going on there with that name. That's a mouthful. All right, so why don't you try some now? It's your professionals, maybe. Go. All right, so why don't you try these 2 to begin with? So top one, we want the name. Bottom one, we're looking for the correct formula. Let's see what you come up with. Okay, so let's take a look to see how we're doing. So starting the first one. So first one here, we do see the bracket right about here. So this is our complex ion part. This obviously then would be our counter ion. And from the location of our complex ion, it comes first. So without even doing it, we do know it's going to be a positive guy. Our counter ion is going to be negative in this case. So we do want to sort of take apart what we got going on here. Because our complex ion is positive, that means that we can use chromium for this name. So we do want to kind of figure out what the oxidation state of chromium is here. So starting with water, water is neutral, so that's 0. Our Cl here is -1, and there's 2 of them. That gives you like a -2. Our counter ion on the outside is also Cl, which is -1. So that's -2, -1 is -3. So the chromium here, to balance it out, has to be 3, which means we're going to have a Roman numeral of 3 happening there at the end. We also have some ligands here. We have 4 waters, and water is aqua or aquo, your choice there. I think your book might use aqua, or you could go O. 4 of them means that it is tetra. So we got tetra aqua or aquo. We also have 2 of the Cl's in the complex ion. So 2 is dichloral. So that is all the components of our complex ion. We do need to put it in alphabetical order. So alphabetical order, of course, is here, A before C, ignoring the prefixes. I don't make the rules, just tell you. So this is tetra aqua or aqua, your choice. Dichloral. Chromium, as the metal comes at the end of the complex ion part. 3. And if that wasn't enough of a name, we still have our counter ion left to name. And we name it just like we talked about before. It is an anion, which means it gets IDE at the end of it. So that would be chloride, IDE. So that's tetraaquo dichloral chromium 3 chloride. Any questions on that name there? Now, coordination number. Yeah. So the IDE part over here, if that is what the question is because it's an anion, right? So just in general, basic nomenclature, just like you did when you talked about nomenclature, if something's negative and it's just an element, right, it usually will end in IDE. So that's why chlorine becomes chloride. So it's sort of the same rule here as well. If you have that negative ion at the end and it's just an element, it'll just have that normal IDE part of it. If it has a polyatomic ion at the end, you would just use the name of the polyatomic ion. So those are sort of the 2 common sort of anion negative guys that would end it, either sort of a element with a negative charge, which will get the IDE, or that polyatomic ion, which then would just use the polyatomic ion name. In terms of the coordination number here, we got 2 Cl's and 4 waters. They are each monodentate, and they are both, all those guys are attached to the chromium, which means the coordination number here would be 6 in this particular case. Any questions on the first one there? Okay, so on the second one, we actually have the name, and we want to basically build the formula. So really the easiest thing to sort of do is just to figure out the parts and sort of put it together. So tris ethylenedyldiamine, tris means 3, and that ethylenedyldiamine, if you remember, is the one that very commonly is used as, or written as EN. And they use it both in the formula and they also use it in the name sometimes. So you don't have to write, you know, CH2, CH2, NH2, NH2, all those guys in there. kind of a shorthand that's used a lot. Tris means we have 3 of them, so we kind of got that going. Cobalt with a Roman numeral 2 means we have a cobalt with a +2. And remember that the metal comes at the end of the complex ion name, which would tell us that all the way through here, the boxing-ish, everything in that big box is the complex ion part of the name, or our complex ion part. That means that these are really the only 2 components of our complex ion, which means if we put our complex ion together, we would put our cobalt in there. We would put our En with our 3. And what's important to remember as well is sort of the charge on your complex ion at this point. We know that the cobalt is +2, the En is neutral, which means that overall this complex ion at this point has a +2 charge. And that's important for when we get to our sulfate here. Sulfate is SO4 2-. So what that tells us is this is -2, this is +2. That tells us in terms of our counter ion, we just need 1 of them, which then when we put it together, will give us the correct formula here, which will look something like this. Any questions on that particular one there? Okay. So let's try a few more here. We got several more to go, I think, just to make sure. So why don't you give the name of these guys here? And you know, while we're at it, why don't we do the ones that we saw earlier? So why don't you do this one as well? Do KAUOH4. And why don't you do CR NH3 6 NO3 3. All right, so why don't you give the names of these guys, see what you come up with, and we'll talk about it in a few minutes. Okay, let's see how we're doing here. So start with the first one. So again, just sort of dissecting what we got going on. We see our bracket up here. So that's our complex ion part. It also comes first, which does tell us our complex ion is positive. This would be our counter ion here, which then would be negative. In terms of the cobalt, because it is positive, our complex ion, we can use the whole name for cobalt. So we do need to figure out the oxidation state on it. So NH3, which is ammonia, is neutral, so that's 0. This Cl over here, that's part of the complex ion, is -1. And we also have 2 Cl's on the outside, which are -1 each. So that gives us a -2 and a -1 is a -3, which means that our cobalt here would be +3. So we definitely got cobalt with a Roman numeral 3 happening. We have 5 of our ammonia in there, and that's going to be penta for 5. And ammonia becomes amine. And we also have a Cl. And remember, chlorine and those halogens become like chloral type of groups. So that is all the components of our complex ion part. Again, the metal comes at the end of that part of the name, and we want to put it in alphabetical order. Ignoring the prefix again, we go with A before C here. So that's going to be penta, amine, chloral, cobalt, Roman numeral 3. Almost out of room. And our counter ion here, which again, even though there's 2 of them, just going to be named like normal, and that's going to be chloride at the end of it. So pentaamine, chloral, cobalt 3, chloride. That just rolls off the tongue, doesn't it? There. Any question on that name? We could do the same thing here. Again, in the brackets is our complex ion, which comes actually second in this case. Means it is going to be negative, our complex ion. Our counter ion here will be positive. So same approach, we want to figure out what the oxidation state is on the iron. Cn is cyanide, which is -1 each. And there's 6 of them, gives you -6. We have 3 potassiums, each at +1, gives you like a +3 happening there. And that means in this case that the iron is going to be +3. Also means that because the complex ion part is negative, we will not use iron for the name, but we will use ferrate for the name with a Roman numeral of 3. In terms of our ligands that are there, we have 6 of the cyanides. Prefix for 6 is hexa. Cyanide becomes cyano. And that takes care of our complex ion part. Again, here, our counter ion, even though there's 3 of them, will be named just like normal. So we will start with potassium for our counter ion. Starting with our ligand here, hexacyano, ferrate 3. Again, the metal coming at the last part of the complex ion part of the name. Question on that one there. Coming down to these 2 that we saw earlier. So if you look back in your notes, we've actually went through the oxidation states of this. And just really quickly, that's -1 for our OH. That's 4 of them. That's +1. So our gold here was +3 in this case. We also see that the complex ion part comes second, which tells us that we are going to need to use not gold, but the sort of old school name there for gold, which is arurate, Roman numeral 3. There are 4 hydroxides. Prefix for 4 is tetra, and hydroxo for hydroxide. And again, here we're going to start with our counter ion just like we did right here. We're going to go with potassium. putting our ligands first, tetrahydroxo arurate 3. Any question on that name there? And lastly, the other one that we saw previously as well, which again, going through the same sort of method there, 0 from our ammonia, -1 for our nitrate. There's 3 of them. So as we saw earlier on in that slide, the chromium here is going to be +3. The complex ion part in this last one does come first, which tells us it's positive. Also tells us that we can use the whole name there for chromium. And it is going to be Roman numeral 3 there. And we do have 6 of the NH3s. So starting with this would be something like hexaamine for the 6 NH3s. Chromium, Roman numeral 3. And our complex ion part here, even though here we do have more than one, the name of that complex, the counter ion there is nitrate, and that's what we would use here. It would be nitrate. So hexaamine, chromium 3, nitrate. Let me see. If I understand your question correctly, we typically we only add 8 if that's what you're asking for about to the metal when it is part of a negative complex ion. So the metal for the complex ion and that complex ion by itself is negative. That's where we do use that 8 part. So how would you know if it is? No, typically it will only be the 8s. In that sense. For the most part, all the complex ions typically will have that kind of higher positive charge for the most part. So usually you'll just use the 8 as the part of it, no matter what it is. I think there were questions. As odd as it may sound, I don't really have an example off the top of my head, but we will see one actually, or there might even be 2 when we get to that lab on Thursday. But you would follow sort of the same process. So for example, like we did here, we started with 0, and then, this was like -1. So for example, if you had, if you went to the outside here and this was -3 for the nitrate, and when you added up everything besides say the metal, and you got a +3 in that case, then it would be 0. So you would work it the same way in terms of, you would leave the metal for the end to try to figure out the oxidation number on it. And then you would, as you would go through, what you would end up with is 0 by the time you get to the metal, which means then it's neutral in that case, if that sort of makes sense. So you would follow kind of the same procedure there to try to figure it out, the charge on the metal. But what you would end up with is, instead of like what we ended up with on the bottom one there, we had -3, and we needed to balance it out to 0 by adding +3. You would get 0 at that point, and there would be nothing to balance. So it does sort of happen. I think there was another question. Let me just look real quick. That's a good question in terms of the complex ion. So the question was, would you have to do anything if there was actually a subscript on the complex ion, which it is possible to have. You could actually have, as odd as it may sound, you could actually have 2 complex ions put together. So, you would actually have like 2 brackets, and they both would be complex ions. So it is possible that could happen, and the short answer is probably no in most cases. You would just kind of look at each of the complex ions sort of separately and name them like they were separate, and then just put the whole giant name together, if that sort of makes sense. So the only place you probably might see something like that, typically the complex ion won't have a subscript in a normal situation like what we're seeing here, because we'll balance it out with the counter ion to make sure it equals 0. But the only place you might see something like that is if, say, you had a positive, complex ion, and it was put together with a negative complex ion. And then, say, in a case like that, you could have something, potentially like, 2 or something like that. Say if this was +2 and that was -1. In that case, again, you would almost just name it like, just take this part of it, the complex ion part, and name it like normal as a positive complex ion. Then you would take this part and name it as a negative complex ion, and then kind of just squeeze both of those names together. That probably would be the only place where you would see a subscript on a complex ion. In these normal situations, you don't see that because the counter ion is there to completely balance out the complex ion. So you don't typically need more than one of the complex ions. Other questions on that? So a couple other things why we got this up here. Coordination number, kind of scribbled out already, but if we look at it in terms of the complex ion, we have 6 for the first guy here. The NH3s are monodentate. The Cl is monodentate, so that gives you 6. Coordination number for our second guy here would also be 6. Again, the Cn minuses. I think we did these earlier. The coordination number of this guy would be 4, and 6 for our last one down there. Any questions on kind of putting those together? We have 2 more, I think, just to finish up here. So why don't you give those a try? So these, we're looking for the formulas for each of these. So see what you come up with, and then we will talk about it. Okay, so let's take a look. And again, when you got the name and you kind of want to do the formula, I think it's just easy to kind of just take the pieces out of the name. So obviously here, just so we can kind of get an orientation, I see platinum 2, and remember that the metal comes at the end of the complex ion part, so that I know this is my complex ion. And honestly, from that point as well, I know that my complex ion is positive because it comes first. And I see the regular name here. And this would be my counter ion in this case. So kind of taking the pieces here, triamine, amine is NH3. And tri means we have 3 of them. So that takes care of like that part of it. Bromol is Br minus. That takes care of that part. Platinum 2 tells me I have a PT with a +2 charge. So now I have pretty much all the pieces I need really to build my complex ion part. So if I pop that sort of into some brackets, and why it's really important to sort of figure out all these sort of charges is when I pop that together and I sort of include my charges, I know that's -1, that's 0, and that's +3. That means that my overall complex ion part, if I just look at the complex ion part, is it is +2. I'm sorry, that's +2. And so it is +1 in that case. It'd be good to use the right number there. So +2 and -1 is +1 overall. And that's important because my counter ion, which is chloride, is -1. So that tells me I just need one of those guys to balance it out. And that would be the correct formula for it. Coming down here, I see potassium, and then I start to see some prefixes and cobaltate 3 at the end. Again, the metal with the Roman numeral is going to be the complex ion part. And there should be, thank you very much, there should be a 3 here. Thank you. Had it here, I just lost it over there. Thank you. So the top one should be PT NH3 3 Br Cl. So when we look at this guy here, our complex ion is negative. And again, we're going to kind of dissect the parts of it there. We have hexafluoral, so that's like a F with a 6. And cobaltate is cobalt with a +3 charge. So again, this is basically my complex ion part, which I could put in brackets, and I will try not to lose any subscripts this time. We'll put a 6 there. There we go. That is overall, though, if we look at it, this guy's -1. So that's -6 and +3. That means that overall, this complex ion part is -3 when it's all said and done. And that's important for our counter ion, which is here. Our counter ion is K+. So that means we don't need 1, but we do need 3 of those K pluses to balance it out. That means when we put all that together, K3CO F6 and look something like that. Any questions on those two? Now, when we look at this coordination number here for the first one is 3 and 1, gives you 4. Coordination number here is 6 in this particular case. Any questions on naming or how to write formulas for these guys? So before we sort of leave the conversation of naming and formulas, let's just talk about what you should do if, perhaps you don't have the coordination compound given to you or the formula, and it's really just a complex ion. So for example, we have this guy sitting right here, and this was all that you were given. How would you go about naming just that? And the way you would go about naming this guy is the exact same way as you would name it if it was in a coordination compound. You pretty much would just leave off the counter ion, which is missing, which means this would be called the hexafluoral cobaltate 3. And it's not a coordination compound, it's still an ion, so people will put ion at the end of it. So if you had to name these guys that were just the ion part, same thing if we took the first guy, which was our PTNH3 3Br, which had an overall +1 charge, we would basically just leave off the counter ion, and this would be called the triamine bromol platinum 2 ion. So if you have just the complex ion part and you need to name it, you basically do it the exact same way. You just leave off the counter ion name, and you follow the same rules as you can see in these two examples. If the complex ion is positive, again, you'll just use the whole name for the metal. If the complex ion is negative, you would use, obviously, the ATE name for it and stuff like that. So we do follow sort of the same pattern if we just have to name just the complex ion part by itself. Any questions on that there? Our naming in general there. Okay. Then we're going to kind of switch gears just a little bit, and we're going to talk about isomers and isomers that involve sort of these complex ions or coordination compounds. So there's several different sort of classes of isomers, but for the most part, an isomer in general, sort of general speaking, is something that has sort of the same molecular formula or the same formula, but basically something's different about it. It could be different connectivity. It could be different orientation in three-dimensional space. You know, it has some differences about it that makes it different than another one that looks very similar to it or has a similar type of formula. So there's a couple different types of isomers that we're going to talk about, which is on this little flow chart here. There are structural isomers, which have different bonds. And sort of underneath that classification, there's coordination isomers and also linkage isomers. And we're going to see some examples of that in just a second. On the other side there, we have some stereoisomers, and stereoisomers basically have the same bonds, but sort of different spatial arrangements. So that's what I was talking about, sort of different arrangements in three-dimensional space. And that creates some isomers, which are sometimes referred to as geometric isomers, which are cis and trans isomers, which we'll talk about what that means in a second as well. And there's some optical isomers, which basically has the ability to sort of rotate plane polarized light. So isomers as a whole generally means that you have something that has the same molecular formula or same formula, but again, there's some type of difference that occurs there, either straight out, they're just put together differently, and they really do make sort of a different compound, or again, although they may be put together very similarly, the arrangement of everybody sort of in three-dimensional space is a little bit different. So let's start with the first type of isomers here, which are coordination isomers. And when you look at coordination isomers, here are two guys. And if you just simply count up everything that's there, we got a chromium in each, we got 5 NH3s in each, we have 1 sulfate and 1 bromine in each. So they are basically made up of the exact same elements that are there in these guys. And this makes them coordination isomers. So the difference between them, though, is this again is our complex ion part, which means, for a very badly drawn example here, attached to that chromium is our 5 NH3s and our 1 sulfate. And overall, this whole entire thing, when you put it together, has a +1 charge. And hanging out on the outside as our counter ion is our bromine, right? So again, this is sort of, maybe not the best drawn, but this is sort of the idea of what's going on here. Again, it's a basic sort of overall ionic compound, and we got these two guys coming together. Now, although the second guy has the exact same elements, the difference is in how it's sort of put together, if you will. In this case, this is our complex ion. And sitting in the middle is our chromium, also still attached to our 5 NH3s. To the nitrogen, by the way. 1, 2, 3, 4, and 5. But now on the inside attached is actually the bromine, which if we take the overall charge going on here, that's a +2 charge for that complex ion part. And that is why we have now the sulfate on the outside that has a -2. And in this case, our sulfate is the counter ion. So although basically they're made up of the exact same of everybody, exact same amounts of everybody, there's actually some difference here in sort of how they're pretty much put together. In the first one, the sulfate is actually part of the complex ion, while in the second one, the bromine is part of the complex ion, and they switch in terms of counter ions. So again, they are definitely related to each other. They will have some different properties for sure because of the different ligands that are attached, and also the different charge that we see overall for our complex ion happens as well. So in the case of the top one, the overall complex ion has a +1 charge, while in the case of the second one there, it has a +2 charge in terms of what's going on. Now, another type of isomer is what is known as a linkage isomer. And in a linkage isomer, much like the name implies, it is actually the atom that binds to the metal is different. The ligand itself is the same, but the actual atom that is doing the bonding to the metal is different. So these are all basically the same things. They both have this ligand here, the NO2-. In the top case, the actual atom that is binding in to the metal is the nitrogen, while in the bottom guy, he is using an oxygen here on the bottom to do the binding in. So again, if you sort of took an accounting of everything that is there, they would all have, again, the exact same numbers of elements, very much of everybody. But what's making the difference here is the actual atom that is attaching to the cobalt in this case. And again, that's why this is what is referred to as a linkage isomer. Again, having that different sort of linkage point, even in the same ligand. So again, both the same ligand, but they have that different linkage point that basically occurs. So coordination isomers, sort of differences in terms of counter ion and sort of complex ion. Linkage isomers, the difference happens within the actual sort of ligand and what is attaching in to the metal. Another set of isomers that we will talk about here just a little bit is what are referred to as stereoisomers. And these can be geometric isomers such as cis or trans isomers. And they basically have the same atoms and the same bonds, but they do end up with sort of different bond angles. And these are very common sort of things that develop in the square planar complex. So if you remember, the square planar is, you know, kind of similar to when you did geometry probably. That's that one where you have the 4 guys basically bonded in a square on the same plane. It's that expanded octet, 6 electron pairs, 4 bonds. That gives you that sort of square planar geometry that occurs. And when we look at an example of this in terms of cis and trans, cis means basically the same side, and trans basically means the opposite side. So you come across cis and trans a lot in organic chemistry if you're going on to take that. And in organic chemistry, what we talk about usually with cis and trans a lot of times is the double bond. So there's a double bond, and either the groups are on the same side of the double bond or they're on opposite sides of the double bond. When we talk about sort of in this sort of square planar geometry, we're talking about the groups being on the sort of the same side of the plane as opposed to opposite sides. So for example, if we look at NH3 and NH3, they're on the same side, right? You can even look at the Cl and the Cl. They're on the same side of the, I don't want to say double bonds, but they're on the same side of the plane, basically, of the bonds. And that is basically what makes this the cis isomer in that case. Trans means opposite sides. So typically your groups are on opposite sides of the plane here. And again, you can kind of see here, the Cls are opposite of each other. And also our NH3s are opposite of each other. And again, that would make our trans. And you can see they both have the exact same formula here. They both are PT NH32Cl. And the only difference would be we would put either cis or trans before it. So typically, you know, they would write something like cis and write the formula there. With it, or put trans in front of it. Here's another example here of a cis and trans, and if we look at it here, this is the trans isomer of this complex ion, and this is this cis isomer of it. Again, you can see the formula here is exactly the same, but it is sort of the orientation in sort of three-dimensional space. So when we think about sort of the guy here, and A is our trans, we look at our NH3s, they're all sort of within the same plane. So you have this plane, and above and sort of below that plane, you have the CLs. So sort of on opposite sides of the plane, and opposite there would be our trans configuration here for our isomer. And that's different than sort of here where our Cl and our Cl have sort of moved to the sort of same side, if you will, of our plane. And that's going to be our cis isomer in here. Again, sometimes very hard to sort of visualize same side, opposite sides. But again, you could kind of roughly think about this all being like a plane. And this is sort of above the plane and below the plane. And here we have not the same group on opposite sides. So when you're looking at cis or trans, typically when you try to do those type of isomers, what you're comparing is the same group being either on the same side or opposite side. So that's why here we have our Cl and our Cl here. And that's why we're comparing those two as being on opposite sides. And that's why we're comparing the Cl here and the Cl here as being that. Yeah, so technically it would be sort of the same thing if you flip it. And once you sort of determine it for one, it would probably work the same for the other. So the question was, you could kind of apply that same theory to the NH3 as well. It would also be very similar as well. It's not actually in terms of, so I'm sorry, I'm gonna make sure I read your question right. It's not in terms of, it wouldn't be trans in terms of NH3 either, because if you flipped it around the top, and I apologize for this really bad drawing, but if you flip that thing around, you basically would have your Cl going this way and your NH3 going this way, right? And you would still have your NH3s like over here, which would still be the same side for the NH3. So it would still be, if you looked at the NH3, still cis, just like it would be for the Cl. That's what I mean. So again, we want to compare the same groups there, but again, sometimes the isomers, the cis and the trans, is really I'll put it that way, difficult in a sense, because it's very hard for a lot of people, myself included, to sort of visualize three-dimensional space and everything sort of happening. So there's also optical isomers, like we talked about as well. And these are isomers that have opposite effect on plane polarized light. And when we have certain molecules that have what are sometimes referred to as being non-superimposable mirror images, these guys are what are referred to as being chiral. And that's basically what chiral means. It means that if you take the mirror image out of the mirror, you cannot take that image and superimpose it on the original image, and it will not fit perfectly. So the easy example of that is your hand, right? If you put up your hand, your other hand is your mirror image. So if you take the other hand out of the mirror, as I try to see what my hands are, as you take the mirror image out, there's nothing you could do to get them to sit perfect on each other. You kind of go that way, go hand to hand, your thumbs are on the wrong side, right? If you go, you know, thumbs on the right side, but one would be palm up and palm down. If you kind of flip them like that, go that way. So there's nothing you could do when you say pull the mirror image of your own hand out of the mirror. Try that yourself. Don't hurt yourself. But if you rotate one hand around to the other, you can never get them to sit perfectly on top of each other where the thumbs match, the palms match, right? Everything's in the right direction. Even if you're triple jointed or something, I suppose you still cannot get it to do that. So you can never get those guys basically to sit perfect on each other. And that's a good example of something that is chiral. If you just pull that mirror image out. So if you take the original guy, put it to the mirror, and then pull the mirror image out. If you rotate it, no matter how you rotate it, how you orient it, you'll never be able to get it to fit perfectly on the original guy. And that's what's known as being non-superimposable mirror images. And that's what's known as a chiral compound. And that compound is basically what is known as, these type of isomers are known as enantiomers. And I think we will stop there for today, actually, before we go too far into this. And we'll finish this up tomorrow. So again, a reminder, we'll have a short little lecture, get through some of this stuff, and then we'll take a little break. We'll take our exam like normal at about 3-ish, and it'll be just like last time. Again, camera enabled, writing it, all that good stuff like we've done before. Any questions on any of that stuff? So again, the content for exam 3 is not this chapter. So I think it ended before this chapter. So again, I think that should be electrochemistry. I think that should be thermodynamics. I think that might be it. I feel like there should be another chapter, but I think that might just be it, those two. So whatever we started, obviously, after the second exam, and whatever we finish before this chapter. So I think those are the 2 chapters. I want to say it should be thermodynamics and electrochemistry. You could double check for sure if you look at the online homework. It'll definitely say exam 1, exam 2, exam 3. But I think for some reason that is maybe the only 2 that should be on there and stuff. So, okay. All right, so make sure you put here if you haven't. And again, a reminder, today we are doing the last group, which is group 4 and group 5. So we'll do it like normal. We'll watch the known video together. Then you'll go off and do your unknown video and, you know, have fun, I suppose. We'll see how he puts his lab coat on today. We'll see how he does that. All right. We'll see everybody in about 10 minutes or so.